Well, greetings and welcome to Naughty Notes. Here we are with the practice exercises for our lesson 111, and that is defining reflections on pages 82 through 84 in your McGraw-Hill illustrative mathematics textbook. Ironically, we've got rotation pictured here, but that's also in the exercise. Let's get to it. Ready? First one. Now, which of these constructions would construct a line of reflection that takes point A to point B? Okay, so I just drew a random point A and B on there, and we're going to go through them one at a time. Construct the perpendicular bisector of AB. Let's check that one out. Well, we know that one. That's our favorite construction. You know, whether we actually draw the segment AB or not, it looks like that. But right there, well, that certainly looks like the line of reflection, because you can imagine if I had this A and if I swung it around like that across that line of reflection, it would map onto B. All right. So I'm liking this one right here. But let's just check them all. Construct a line through B that's perpendicular to AB. Well, hang on a second. That construction is going to look like this. And you've done it before. All right, I'm just going to slide it over so you can see it in all its glory. But that's the construction. That's the construction of a line perpendicular to a given line through a point on that line, in this case B. So that was a little bit different. Remember we said it looked like that old CBS logo. Or if we did it with arcs, it would be the egg. Okay, so I'm going to say that's not going to work. You can't reflect. If you reflect from A across this line, you're going to end up over here. So that one, I say, no good. So let's see what else we've got. Construct the line passing through A and B. Well, that's silly. I mean, I don't think that gives you anything. If you reflect across that, neither of those points move. So no good. And construct a line parallel to line AB. Well, I guess, I can't see how that's going to help anything, because that's not going to map A onto B. The clear winner here was right there, the very first one. The perpendicular bisector of the segment AB is the axis of reflection for A. Well, if A was the pre-image to reflect onto B, or vice versa. Okay, that's one down. Page 82 we're on. All right, I like this question. I'm starting to like some of the stuff in this book. It's just hard to get used to it. That's dinosaurs. A point P stays in the same location when it is reflected over line L. What can you conclude about P? Well, first off, this is something we know, that the image is the same perpendicular distance from the line of reflection as the pre-image. So if I move this around, I see that relationship always stays the same. And of course, the only way P could finally actually map onto P prime, what can you conclude? You put it in your own words. It's got to be on the axis of reflection. Bingo. I like that one. Okay. Let's move it up to here. Oh, I always like these. So what's Noah saying this time? A 180-degree rotation. Lines L and M. I've got line L in blue and M in green. So they are perpendicular lines, and they intersect at point P. And Noah says a 180-degree rotation with center P has the same effect. All right, first off, let's show a 180-degree. So that means that you're spinning around like that. Now, one thing about a 180 degree, I gotta pull up my ray tool. If just a side note there, if you were to draw from A through the center of the rotation, it will go through. It will go through the image on the other side. That's a property of a 180 degree rotation. That's kind of cool. Now, if I just plain flip it across the line M, well, I think A prime is going to end up over there. It's just going to do that. Now, you're looking at this and probably guessing, well, what if I flip it again from A prime here to, I guess that would be A double prime across L, and that is a fact. If you make a composite transformation, a reflection of a reflection, in this particular case, it will be the same, exact same as a rotation. That's kind of cool. But the answer to this question is no, because very clearly a 180 degree ends up in the opposite side over here. If you thought of these as quadrants, let's say if A is in the first quadrant, A prime, or this A prime, the reflection here is in the second quadrant, but the 180 degree rotation is in the third quadrant. Okay? All right, next page it says on the bottom. I can get used to this. All right, I was too lazy to make the diagram, construct the diagram from this, but I'm looking at it and saying, which of the following is not a rigid transformation? Now, the fact is they are all transformations. It looks like A looks like a glide transformation, or vector as we like to say. B is clearly a reflection. Now we'll come back to C, but D is a rotation. And I guess you're sliding it over too. But this one, C, is a transformation, but that's a dilation. Now, a dilation can make something bigger or smaller. That means that those two are the same shape, but not the same size. So C is the one that does not fit in this example. Again, it's a transformation, but it is not rigid, and therefore it can't be used. We can't use that in sequence to demonstrate congruence. I think that's where they're really going with that, right? Vector, reflect, rotate, like it. Now this one had me going because, I got this image in my textbook. But then I see that you guys got this image, the one on the left, in your textbook. So, sorry about that. Well, I guess I caught it. So if you take this and rotate it, they're saying, well, where would D end up? Well, this example is way too easy because this D prime is going to end up in the middle of BC. So let's do, this one is always an attempt to be a little more challenging. If I take this, oops, don't mean to be tracing that, and I'm going to slide this over, get rid of that trace, and I'm going to rotate it. Now remember, that D would have been here. Where is that D going to go? Let's put it back here, our D prime, and it's going to end up down there. That makes sense. Okay, so that's a sequence of rigid transformations. And by the way, that sequence in all these cases, well, it's going to be two of them. Here we're doing a vector or a glide or a slide transformation and a rotation. And I think that came out about -47 degrees if you're curious. And that's it for the next page. Let's go. Oh, gotta go this one first. A little review question here. 3 points on the plane. How do we know if Charlie is closer to A or B? Well, the classic, and this, you never forget we're just gonna do this one on the computer. We could draw the segment between A and B. We don't have to, because we could just do the perpendicular bisector construction this way, and I've got to grab the line tool. I'm off the screen on the bottom, sorry about that. And I do like that. See whether or not I've actually drawn the segment AB. That's still the perpendicular bisector construction. If we're on this side of the perpendicular bisector, we're closer to B. On this side, we're closer to A. And that's all there is to it. Now, actually, let's have a little fun with that. You know, if we did draw the segments, and this doesn't, I haven't heard this mentioned yet, for vocabulary, if I do this, if I put C on the perpendicular bisector, anywhere on there is going to yield an isosceles triangle, which is kind of nice. I haven't seen that word in our textbook yet, but I know it's coming. And of course, this magic point yields an equilateral triangle. So think about the statement here. Any point C on the perpendicular bisector is isosceles, or makes an isosceles triangle. Does that mean that this is isosceles? Yes, because equilateral is isosceles. But as you can see, isosceles is not equilateral, because that would be a sometimes, and sometimes means no. So let's go to the next one. Quadrilateral with 4 congruents. Got a little 1 in there. Get rid of that. Diego says this is a quadrilateral with 4 congruent sides, which we all know is a rhombus. So let's write that down because, you know, it's a rhombus. All right. And it says, let me see. It says it's always regular. Well, we know what regular is. Regular means equilateral and equiangular. So we know Diego's not right. But Maya says it's never one. Well, can it be? Well, you know, I want to demonstrate this a more interesting way. Let's draw this. Do yourself a favor. If you have a rhombus, I'm going to draw the diagonals. Now, because these diagonals meet here, they're actually the perpendicular bisectors of each other, which is really cool. Oh, I want that circle. So that means if I draw a circle here, I can also draw a circle here. Now all 4 vertices are on 2 different circles. Watch what happens when I tip it like this. Closer, closer, closer. Farther, farther, farther. Now, a property of all regular polygons is that they're all inscribed in a circle. Now, any polygon inscribed in a circle doesn't have to be regular, but if it is regular, it is inscribed or can be inscribed in a circle. So in this case, the square is inscribed in a circle. The rhombus is not. And I think that's all there is to it. But let's just write another statement here. A square, get us used to this logic, is a rhombus. Because a square is an equilateral quadrilateral. But I must say that a rhombus is sometimes a square. Now, you will often see that written this way because we'll say a rhombus is not a square. If you're given 3 choices, this means the maybe, sometimes or maybe. But most definitions you're going to encounter, it is a binary choice. It's a square or not a square. If it's only sometimes a square, then the answer is no. So all three of these state, in that context, this is a statement that you may see when we are writing our more logical statements that come in the future. So I thought I'd really digress on that because I like this. I like this little exercise here. So there's another way to think of your rhombus. And with that, I think we're going to close out and see you in classroom. And thank you for watching 90 Notes.